Yes, here we are at the physics video lecture once again. It is Psci 168, video lecture 34. So we're talking about electricity and magnetism now. Electricity first, then magnetism. And we made a huge step last time because we're already talking about currents and power, and we're really ready to talk about household circuitry. The only reason we could have moved that rapidly is because we already had quite a bit of understanding of energy and the whole conceptual framework. I'm going to do a quick review of what we did and then just take it into some basic circuits, useful information for the household even. Good. So we're talking about electricity, and let's just list what we know. We have charge, electric charge. This is static electricity. Electric charge comes in positive and negative. Well, how about we do this? Electric charge, we give it the letter Q often enough. The units of Q are the coulomb. And it comes in positive and negative. Okay. So electric charge. So the second we're going to write plus and negative, positive and negative charge. And then we have the interaction. The interaction is the force law. Interaction, and what is that? That the like charges repel and the unlike charges attract. Like charges repel, unlike charges attract. Well, there's a force there, okay? So force, when you have an interaction, that's just another way of saying there's a force. And of course, if there's a force, then you have force times displacement, you have a work, and once you have that, you have energy, okay? And I'll make that as my fourth point, okay? So three, so the fourth point is work is force times displacement, Newton times meter is a joule. Here, we had the energy is equal to the charge times the voltage. The charge times the potential drop. So yeah, we're talking about energy here. Exclamation point. So yeah, we had charge times a voltage drop or a potential drop. The thing that's most important to remember here is, you know, we've got that unlike charges attract. We have charge separation representing work. In fact, if we take charges and do work on them and separate them, that represents energy, and we can store that energy. So let's go ahead and, so energy, charge times, this is, I'll just write voltage, and I'll put here note, charge separation. At the stage that we're at, that was our only example of energy, was the charge separation. Etc. Good, that one's good to put a box around. So from here, it was just a hop, skip, and a jump to the power discussion. I'll keep numbering. So the next thing we would put in our list here would be electric current. And it's just going to be letter I, and that's charge per time. I'll just write Q divided by T. The units are the coulomb per second equals the ampere. amp here, or amp for short. And yeah, for the electric current, we can just imagine we have, say, a bunch of charges, and they're going in a certain direction, right? They're moving. Now there is a convention that the direction of the current arrow is pointing in the direction of the positive charge, even though the electrons are usually what's flowing and they're negative. But nothing to worry about. The convention is positive direction is the arrow for the current, and that we'll never have any problems, okay? So good, we have an electric current, and from there, we immediately obtain what we ended up with last time, which is power. So power is work over time, or energy over time. And when we did that up there, we had P is equal to Q over T delta V. And then since that was our current, we ended up with this nice formula I delta V. We get the box. And this is the one you should never forget, because these are watts, these are amps, and these are volts. That's something you have around your household even. So directly underneath, we'll even write that watts equals amps times volts. And that's something that's really practical to know, as I'll show you in a little while. So that's as far as we had gotten, and we were able to move that quickly because we had seen this type of a formula before. We were able to relate it to our hydropower formula, where we had kilograms per second and a height, okay? And this voltage is also referred to as a voltage drop, so the analogy is really nice. Okay, and I'm always going to use a delta V in our expressions for voltage, because then I can say delta V equals 12 volts. Example. So let's put the example here under 4 once again. Delta V equals 12 volts, right? So the V is the unit volt. 12 volts. The V is the unit volt, and the delta V is the voltage drop, or the voltage difference. Okay, good. So now let's set up the really basic circuits to pursue this a little bit more. So the simplest example is going to be a battery and a light bulb. May have had that up there last time. That's what we're going to start with and continue a bit. In fact, yeah, we did have a battery and light bulb. Let's set that one up again and have a closer look at it. So, simple circuit. Battery and light bulb. So I'll do it in two ways. I'm going to draw the picture of it. So for my picture, I'll draw a car battery type of battery. And then we can say delta V. It's a 12 volt battery. Okay. And we're going to send a wire up to an incandescent bulb. So there's the shell, and there's a bulb. And if you ever look closely at one of these bulbs, you have to bring a wire into the tip on the bottom and then touch a wire to the shell on the side. These are these threads that you'll see on a light bulb. This is the kind of light bulb you can screw in. It has a very thin, very thin wire inside, and the circuit goes like this. It goes from this tip here to the wire here on the left and then out there. So what is it about this wire that makes light? The wire is very thin. There's something called resistance I'll go into, and the wire simply becomes extremely hot. It can become so hot that it gives off light. So really, it's a thermal problem here, a thermal physics problem. We'll get to that as well. I'll give this a little radiance in my picture. Okay, so it's giving off light, and the formalism tells us we go from the plus to the minus terminal and we draw the currents this way. Okay? So we've got our 12 volts and we have a 60-watt incandescent bulb. So let's say we have a 60-watt incandescent bulb. We have to start with these because of the concept involved. These days we can get light bulbs that give off as much as a 60-watt bulb, as much light that only use maybe 10 watts, okay? They give off much less heat, okay? But the principle here, in terms of the use of energy in the circuit, is the same principle. Here it's very, very direct. That filament, let's say filament, it's a very thin piece of tungsten. Normal metals would melt at these temperatures, so typically made out of tungsten. Filament gets very hot, it gives off the light. We've got 60 watts, and 60 watts, of course, is a power rating. Most of that power is just going into heat. The light is just a byproduct, so to speak. Okay. So we have from our formula here, P is I delta V. So from P equals I delta V, we solve for I is P divided by delta V, and I chose some nice numbers, but they're also realistic. 60 watts divided by 12 volts is equal to 5 amps. Okay. So that's a nice example. Light bulb circuit on your car. Okay. So we're going to represent this thing schematically now. So it's the same picture. So this is going to be the schematic diagram. And here we represent the battery with two plates. So remember those parallel plates on the capacitor, their symbol, which we're not going to need anymore, would have been equal length plates. But if you have unequal length plates, the long side is plus, the short side is minus, and we can just say it has some value for delta V. And then we connect our wires just like we did up there, except instead of drawing a picture of a light bulb, we're just going to have a little jagged line like that labeled R. So R is the resistance and at the same time this object is a resistor. Okay. The unit of R is given by an uppercase Greek omega letter, and that's the ohm. But yeah, what is a resistance or a resistor? Well, if we go back here, it was that light bulb that got very hot, and that's what a resistor does. It gets hot. It uses energy and gives it off as heat, or dissipates it as heat. So yeah, the resistance, you can think of it in a certain sense as friction. The current, the charges flowing here, they encounter a lot of resistance because the wire is so thin, and in being forced through that very thin wire generates a lot of heat. A lot of collisions going on generates a lot of heat. So that's the equivalent circuit here. Maybe I should draw the current I, which goes from plus to minus. Okay. So we have the same labeling over here as we do over here, except we've introduced this new quantity, the resistance. And beyond its units here, there's a law that goes with it called Ohm's law that we also have to know about. So this next topic we'll just refer to as Ohm's law. Okay, so Ohm's law. And by way of commentary on that, I'll just put down what I said here. The current encounters a resistance, some kind of friction in passing through this circuit element, in that case the light bulb. And it uses energy to do that. So Ohm's law relates voltage, current, resistance. So we have delta V is equal to R times I. So your voltage is equal to the product of the resistance times the current. We can use that to get the, first of all, the units of the resistance, and then we'll do some applications here. So for a given battery, higher resistance, lower current, okay? Lower resistance, larger current. So let's put this as a node. We have R equals delta V over I. So in terms of the units, we have volts per ampere, and that is the ohm. Okay. Because these units are all just consistent. And these units also are the ones that go with our kilograms, meters, and seconds, and so forth. And yeah, I should even point out, remember, everything is going to reduce to kilograms, meters, seconds, and coulombs. Okay, and with everything that includes this resistance here. If you were to go to volts, and you look at the definition of the volts, you would have joules per coulomb, right? And here you would have coulombs per second. Okay, so it would all reduce back to our original units, but now we have 4: kilograms, meters, seconds, and coulombs. Okay, so much for that. So we've got Ohm's law, we've got this relation here, and you know, we can apply it up here now, because you know, there was a certain unknown up there because we were just using the power formula. Now we could look at that circuit and say, well, if we have the voltage and the current, what is the resistance? So let's continue this example. So in our previous example, we had 60 watts, etc., etc. But we had delta V equals 12 volts, and I is equal to 5 amps. Okay. So what does that tell us about the resistance? Therefore, the resistance, and I'm talking about the light bulb, okay, is equal to this delta V over I would be 12 fifths ohms And what's 12/5? That's 2 2/5, 2.4. Okay. 2.4 ohms. I'll write the ohms out. Okay. Uppercase omega, or you can write out an ohm like that. Okay. Now we have to be aware of this, although in our household wiring we don't really care that much what the resistance is, but I'll show you why we definitely need this law. So what we can do next is combine these two laws. Where's the second one? These two. Okay. So let's go ahead and send that up and do this next. Now we'll combine them right here. We've got room. Okay. So now we're looking at the power formulation. I'll write this power and resistance as our heading. Now we have the power formulation, P equals I delta V. But now we can take the delta V equals Ri and plug it in, and we get I times R times I. So the one form of the power, we'll put a box around this, P equals I squared R. And there's a second version of this. They're both very useful. We can also write, here, how about red, P equals I delta V, but now we're going to solve for I in this equation. So that'll be delta V divided by R, so we'll have delta V divided by R times delta V. And this version is P equals delta V squared divided by the resistance. Okay, so what's important about these formulas? Not so much the resistance at this point, but the dependence on the current. So say I'm sending a current through a circuit, okay? Current through a circuit here. If under some circumstances I double the current, okay, because the current is squared here, I'm going to quadruple the amount of power used, okay? So if you double the current, you quadruple the power. But what is this power representing? It is representing heat, okay? And in our schematic, we're only letting the heat be generated by the resistor. Now, in reality, everything's going to generate a little bit of heat, and suppose these wires are the wires in your wall, okay? And if they start to get hot, you can have the problem of starting a fire. Okay? So the relation of current and power is really important for that reason. And I should point out, the ideal circuit, this wire has no resistance, and it's all in the light bulb. In reality, the wire itself has some resistance as well. The wire can get hot if too much current flows through it. Good, so that takes us right into some practical household wiring examples. I'm going to consult the clock here. Yeah, we'll move to some household wiring. Send this up now. And I'll make some notes of all of these things I just said. Yeah, we've got the schematic. Well, we'll replace all this with a new picture. So we'll basically redraw these pictures here. Let's see. So let's call this household wiring. First of all, the household electricity is an alternating voltage and current. We haven't gotten there yet. Our batteries are direct current. We're going to have to study magnetism to get to the alternating current, but the formulas are going to be the same, so we don't have to worry about that, but I will make a note of it. Household wiring. So the first thing we'll talk about here is direct current, and that comes from things like batteries. Okay. And I'll even draw a couple batteries here. So you've got your little ones and your slightly larger ones. So your A, C, and D cell batteries, right? You've got those kind of batteries. These are generally delta V equals 1.5 volts. If you put them end to end, you can just add the voltages. So if you have 1.5, 3 batteries end to end would be 4.5, and so forth. Okay, so you've got those. You've got the little box-shaped battery with the 2 terminals that you put into your smoke detectors and things. Okay, these are 9 volts, and I'll go ahead and put the car battery here as well. Have a look in your car. You know you've got 12-volt battery. That's all direct current, and the circuits we've been talking about, in particular this delta V are covered by that. So we can even draw the current. And we have those formulas. Now, alternating voltage and current, we're going to very carefully study it in the coming hours because we have to study magnetism in order to properly discuss that. And that will allow us to understand motors and transformers and generators and things. But the formulas are going to be these same formulas, okay? And including this one. So let's go ahead and briefly mention that alternating voltage / current. What we're going to use is a symbol. Instead of a battery symbol, we're going to use a symbol like this, and we'll say delta V. For the household, it's typically 120 volts. Okay. So normal plugs, I'll call them plug circuits, and light circuits in your household have delta V equals 120 volts. So I'll erase the 120 right here. That's just the delta V. Your range, your air conditioner, maybe your clothes dryer have 240. Okay. So range, air conditioner, dryer, delta V equals 240 volts. Okay. But it's alternating, so it's not constant. It goes like this. It alternates between plus and minus. But how that happens we'll talk about after we study magnetism. For the moment though, we have to know these formulas and the fact that these voltages obtain in order to talk about the currents and stuff. Okay. And we have both of them in the household, but these are little small, small portable appliances, and these are the real heavy-duty ones. Okay. So now I'm going to come back to these power formulas and remind us that the wires can get hot as well. So let's call this point 3 and consult the clock. We'll end with this. Yeah. So these simple circuits are idealized. A simple circuit is an idealization. We'll just draw it again. So since we're talking about household, maybe we'll do this. Delta V, but we still have a resistor. Actually, a lot of interesting details that go beyond what we're doing, okay? But we're going to use just the basic formulas. So good. In fact, you can see my arrows don't really make, oops, that was a mistake, don't completely make sense anymore, because not only is the voltage going to change, the direction's going to change so and so many times per second. Yeah, let's even note this right here. Frequency equals 60 hertz. But that's just for completeness. We'll get that later when we study this stuff in depth. Okay, back to this idealization. So what's ideal about it, what's idealized about it, is we're claiming that the wires are ideal, they have no resistance, and all the resistance is in the light bulb. Okay. But, in fact, the wire is a length of copper. The light bulb is a little bit of tungsten, but that copper also has some resistance. So the idealization is namely that all resistance is in the bulb. And what that's meaning is, what that's saying is that all the heat is generated in the bulb. Hence, only the bulb gets hot. Exclamation point. In reality, the wire can also get hot. Okay. So, in reality, the connecting wires can also get hot. And if they get too hot and they're buried in your wall, you run the risk of a fire, some kind of meltdown. And what's interesting in terms of the power used, remember we have power equals I squared R. So sure, we were just applying this, say, to this resistor here, but it actually also holds true for the wires. So you could be generating power in the light bulb plus some power in those wires, namely they're just getting hot. So this is the formula that tells you, if you know the resistance of your wire, this will tell you how much heat is being generated by the wire itself. And the upshot of that is you actually have to build a circuit breaker into your circuit so that if the current is too large, the switch will switch off and you'll avoid damage, for example, a fire. We'll talk about that next time. Everybody has a panel, an electric panel in or on their house somewhere, And that's where those circuit breakers are located. Okay, but for now, we have this. We'll get a homework assignment next time. So next time we'll go a little deeper into the household wiring and we can come up with some good examples for you. Okay, good. See you then.